Now we look into the working of BJT. The circuit diagram for the BJT is as follows, and using this diagram we'll understand the working of BJT. So we can see that the base and emitter junction is being forward biased, and the collector and the emitter junction, or the collector and the emitter junction over here, is being reverse biased. And we can see the resistance RB, which is present between the base junction and the battery, and RC between collector junction and the emitter junction, sorry, the battery VCC. And VB is the potential difference across the base junction and the emitter junction, and the VC is the potential difference across the collector junction and the emitter junction. So these are the symbolic, or the symbols, what are being used in order to understand the working of BJT. We look into it. So VBB is the source voltage for the base, and VCC is the source voltage for the collector. VCC is the potential difference across the base and the emitter terminal, that is VBE will be equal to VB minus VE, and VCE is the potential difference across the collector and the emitter terminal, that is VC equals to VC minus VE. And these VB equals to VB minus VE, and these are the points which are just made to understand what VB and VCE mean. They don't literally mean what, that's not the real formula for it. Formula is something different, and this is just to understand what VB and VCE means. So don't get confused with that, and let's understand the working of it. When the base emitter junction is forward biased, the potential drop across the base and emitter is approximately equal to 0.7 volts, that is VBE is 0.7 volts. When BE junction is forward biased, electrons from the emitter will be pushed towards the base terminal. This is because emitter is heavily doped, hence electrons move from heavily doped region to lightly doped region. And it says that the electrons from the emitter region will be pushed towards the base region, because we know that the negative part of the base emitter base junction is connected to the negative terminal of the battery, and the positive terminal of the battery is connected to the base junction. So the electrons from the negative terminal of the battery is going towards the negatively charged emitter, or the n type of the emitter, and that region becomes electron rich. And we can see that this region is heavily doped, because it is, the n type is due to the formation of the intrinsic semiconductors which are being doped using pentavalent atoms. And when we dope an intrinsic semiconductor with a pentavalent atom, it becomes rich in electrons due to the formation of free electrons, and thus this region, the emitter region, becomes electron rich when the electrons from the negative terminal of the battery will move towards the emitter region, and thus the emitter region becomes heavily doped. And we know that the electrons will usually move from the heavily doped region to lightly doped region. And here, as I mentioned earlier, the base region will be lightly doped. The emitter, which is being heavily doped, has majority number of carriers, that is the electrons, and these electrons will move towards the base region, which is lightly doped. And the other reason you can say is, the base region is being positively charged, and the positive charges attract the negative charges, that is electrons, and these electrons are present in the emitter region. Thus we can say that the free electrons which are being formed in the emitter junction will be dragged towards the base due to this reason as well. So Here it says since emitter is heavily doped, the emitter has majority carriers, that is charge carriers, and because it has more number of electrons than the base region, once the voltage is applied, the electrons will start moving towards the base region. As I said earlier, the heavily doped region, the electrons from the heavily doped region will tend to move towards the lightly doped region, and thus we see the movement of electrons from the emitter junction to the base junction. And as the let us look into the further, as the electrons enter the base region, they can have two pathways. As you can see in the circuit, there are two chances for electrons. Either they can go towards the collector region, or they can come back towards the resistor RB and go back to the battery itself. But let's look what happens for the majority number of charges here. And they can have two pathways. One, they can go towards the positive terminal of the voltage source, or they can go towards the collector region. And most of the electrons go to the collector region. Since the base this is because, let me explain it later, since the base region is not heavily doped, it cannot create enough holes for the electrons entering the region. Therefore, electrons go towards the moderately doped collector region. So what happens is, here the base junction over in the base emitter configuration, what happens is the base junction is not heavily doped, we know that, and since it's not heavily doped, it cannot create enough holes for the electrons, so that the electrons coming from the emitter region can go and occupy these holes. So what happens is, since there are no holes for the electrons to go and fit in, the electrons tend to move towards the collector region. If there were enough holes in the base region, they would have gone and occupied that space, but it is not happening here. So what happens is, the electrons will go towards the collector region due to this reason. And even due to the small width, we know that base junction is very small in width and very thin, and the electrons entering in this region will easily escape that small width. So the probability of electrons being captured in the base region or occupying these holes is very less due to this reason. So we can conclude that due to this reason as well, base region, even due to small width of base region, the electrons entering the base region will easily able to escape the base region and enter the collector region in order to fill the holes in the collector region. Okay, and since the collector region is reverse bias, we know that the positive terminal of the battery, that is VCC, is connected to the negative, that is N type of the collector, making it reverse biased, right? So since the collector region of the reverse biased, the electrons entering the base region are easily attracted by the positive charges. That is, the positive charges coming from the positive terminal of the battery from VCC will create holes in the collector region. And we know that the width of the collector region is also very high, where it's bigger than the base and emitter both, and thus making it create more number of holes, so that the electrons coming from the emitter region can be collected over here. The electron comes to the base region and it escapes that base region and it gets collected in the collector region, where holes are being created in large number. So what happens is, the electrons entering the base region are easily attracted by the positive charges coming from the voltage source. Hence we see the flow of electrons from the base region to collector region, and hence we see the flow of charges in the BJT for active region. Okay, and as you can see in the circuit diagram, there is a flow of electron from the emitter region to the base region, and due to the positive charges coming from the battery, we can see that holes are being created in the collector region, and as holes are being created, we can see the flow of charges in the collector region, and the positive charges coming towards the collector region will also attract these electrons, and thus we see the flow of charges in the active region of the BJT, and very small amount of electrons go towards the VBB region, while in the base region, that is, as I mentioned earlier, that is, there are there's a very small probability of electron going towards the positive end of the source battery of VBB, and most of the holes direction flow in the opposite to that of the electron flow direction. That is, as you can see here, the holes which are being created will usually be in opposite direction of the flow of electrons. Only in that case there is a possibility of electron being captured, or electron can occupy the holes which are being created in the BJT. So this is the working of the BJT, and now we look into the current in BJT. So what happens is, as you can see the circuit diagram, by now you could have guessed like what the working of BJT is and how is the flow of current in the BJT. So current flow is usually in the opposite direction of the flow of electrons, right? So we know that the electrons flow towards the collector region, and from there it goes towards the positive source of the VCC, right? We will be applying KCL such that we can say that IE, the current in the emitter junction, is IE, and it is the sum of IB and IC. And we know that, as I mentioned earlier, there is a very small number of electrons flowing towards the positive source of the VBB, right? So if the electron flow is very small, the chances of current flow is also very less. So we'll be approximating IB to be 0. Okay, so, and thus we can conclude that IC is approximately equal to IE as well, and that is, we will, using a constant called alpha, we'll write it as IC equals to alpha IE. Alpha gives the fraction of emitter current flowing through the collector terminal. Okay, and we'll be substituting that value IB in the first equation, that is IB plus IC equals to IE. Over there we'll substitute the value of IC as alpha IE, and later by some small simplification we will arrive at the equation where it says IC equals to beta IB, right? And here we have written that IC equals to alpha by 1 minus alpha, which will be considering it as in some constant beta, and later we'll write that as IC equals to beta IB, where beta gives the current gain of the BJT, right? Current gain of the BJT, and we can say that as an amplification factor. That is, by what factor the current in the BJT, that is, the IC value has increased. The IC value has increased. That is what beta gives you, and later we have substituted the beta value in the same equation, IB plus IC equals to IE, and after substituting IC value as beta IB, we have got that IE equals to beta plus 1 IB, and it is the relationship between the emitter current and the base current. This particular equation is the relationship between the emitter current and the base current. This is what, and thus we obtain the relationship between the collector current and the base current, and collector current and the emitter current, collector current and the emitter current relationship is over here. You can see that as IC is equals to alpha IE. That is the relationship between current of the collector region and the current of the emitter region, and this is IE equals to beta plus 1. IB is the relationship between collector current, sorry, the current at emitter region and the base current. This is all about the current in the BJT, and here we have even looked into the working of BJT as well.